In this video, we're going to look at waves and electromagnetic radiation. There we go. So, first, properties of waves, properties of light. There are two main properties that we're going to work with in this class. One is the frequency, and the other is the wavelength. And as you might be able to tell from this diagram, they are related to one another. So when we look at this wave right here, the wavelength it's just the distance between the peaks. And you can see right here, there's a very short wavelength, very short distance between the peaks in this wave. Compared to this one down here, where there is a longer wavelength, there is more space between the peaks. And this is actually measurable in simply length. So for example, it could be in meters or nanometers. It's commonly measured in nanometers if we're talking about visible light, but at the very least we've got meters or maybe nanometers. Now, what is frequency? Frequency is a little bit harder to wrap your head around, I think. Right now, this is like a still image, but you might imagine a wave kind of propagating through space, moving along. And so if I just put my finger right here, there's a peak right above it. Okay, so if this wave is propagating along, frequency is essentially how many times does a peak pass by this point per second. So in this case, because the peaks are close together, it's going to be many times per second that the peaks pass by this point. And in this case, well, fewer times per second, because there's more distance between the peaks. So frequency is measured in what are called hertz, Hz. Also, it's, as I said, sort of cycles per second. For some reason, the cycles are eliminated from the unit, but you can say inverse seconds, also 1 over seconds. Those are all the same thing, ways of saying the same thing. But whether it's hertz or inverse seconds, expresses s to the negative 1 or 1 over s, we're just talking about cycles per second. Now, we're going to look at the electromagnetic spectrum, which is really, really interesting because there are so many things that you've seen before, or heard of at least, that fall into the electromagnetic spectrum, and fundamentally the same stuff. So for example, radio waves, AM or FM radio, electromagnetic radiation. Microwaves, like what you use to heat up food, electromagnetic radiation. Infrared, you may know of like night vision goggles. They are able to help you pick up the infrared radiation that people or animals, living things give off. We actually are radiating energy ourselves as we speak. Now, you don't see it as visible light because it is outside of our eyes' ability to see. But we give off infrared radiation. There's also ultraviolet radiation, which comes from the sun, in addition to lots of other radiation that we get from the sun. But that's the dangerous stuff. It's high energy, it's high frequency, it's low wavelength. It is something that causes skin damage, right? X-rays are also something that we have to be very careful with. You may if you've ever had a broken bone, you had an X-ray scan, that's to help a doctor see whether you've broken a bone. But you want to be very careful about not being exposed to X-rays for very long because they can be also very damaging. They are very high energy. And then finally, there's gamma rays, which, if you have heard about them, you'll only ever see them in the context of radioactive materials. They're extremely damaging. Notice that the more dangerous stuff, UV, X-rays, and gamma rays, well, they're all at the shorter wavelength, higher frequency end. versus radio waves are very, very long wavelengths. We're talking many meters or tens or hundreds of meters even. And of course, there is the very narrow range of visible light that we're capable of seeing, from red. Hey, look, it's the rainbow, Roy G. Biv. Right? That fits in here. And notice that infrared is just a little bit past red, and ultraviolet is just a little bit past the violet that we see. So, the relationship that we have, you may have noticed long wavelengths, low frequencies, short wavelengths, high frequencies. Well, the actual exact relationship that we have is that wavelength, known as lambda here, times frequency. I know that looks like a V, but it's a Greek letter nu. So lambda nu is equal to c, the speed of light. For a terrible physics joke, if you ask a physicist or some chemist, what's new? What's new? They may respond, c over lambda. Didn't say it was a good joke. So wavelength times frequency is equal to the speed of light. We will need to know what the speed of light is. That is 3.00 times 10 to the 8th meters per second. And wavelength and frequency are measured in meters. Meters. And frequency in inverse seconds. There we go. So let's say we are given a question. Cordless foam operates at 5.8 gigahertz. What is the wavelength at which it operates? So we know, let's see, gigahertz, that's hertz. So we know that nu, our frequency, is equal to 5.8 gigahertz. And we're trying to find lambda. And there is that equation C equals lambda nu, or lambda nu is equal to C. So I'm just going to write lambda times nu is equal to C. And I can actually rearrange this because I know I'm solving for lambda. So I can say lambda is equal to C over nu. Trouble is, I've got 5.8 gigahertz. So I'm going to actually have to convert that to hertz, which is entirely manageable. If we go back to our metric conversions, we might know that 5.8 gigahertz times how many hertz are in a gigahertz? 10 to the 9th. But is it 10 to the 9th hertz in a gigahertz, or is it 10 to the 9th gigahertz in a hertz? Well, hertz are small, gigahertz are big, so we know there are a lot of these little small hertz in 1 gigahertz. So what we end up with is 5.8 times 10 to the 9th hertz, which actually, for the sake of making the units look better, I'm going to say is 5.8 times 10 to the 9th inverse seconds. I'm sorry about the pen here. All right. So we can say lambda is equal to C over nu. Our speed of light is 3.00 times 10 to the 8th meters per second. And we're dividing by 5.08 times 10 to the 9th inverse seconds. Or another way of expressing that would be that we have the numerator as meters times seconds to the -1. I'm going to cancel these out, and we end up with lambda being equal to, if I go to my calculator here, we have 3 times 10 to the 8th divided by 5.8 times 10 to the 9th, and we end up with 0.0517 etc., meters. But since I have 2 sig figs here, I'm going to have to cut it off at 0.052 meters. And that's how I make a calculation, converting from a frequency to a wavelength.